Myself, Karanam Narayana, Assistant Professor, Vijayanagara College, Hosapete. Now in this session we shall understand the stationary longitudinal waves in a rod. Consider a rod AB of length L and P is a point at a distance x from the point A and is at a distance x dash from the point B, which is represented as shown in figure. Consider a plane longitudinal wave traveling along a rod or AB of length L with the end A taken as origin of x-axis. Let the displacement of a particle P of the rod at a distance x from the origin is given by y1 is equal to a sine 2 pi by lambda into Vt minus x. Let us call this as first expression, where lambda is the wavelength of the wave and v is the velocity of the wave. Then the displacement of the particle at the end B of the rod is given by, as the point B is at a distance x is equal to L, therefore on replacing x by L here, we get the displacement. Therefore, the displacement is y1, that is equal to a sine 2 pi by lambda into Vt minus L. Let us call this as second expression. If the rod B of the rod is free, then the position or the positive displacement is reflected as positive. As the positive displacement is reflected as positive, and hence equation also represents the equation of a wave originating from B and traveling in the direction of BA. If the distance is BP, that is equal to x dash is equal to L minus x. So from figure, the distance is BP, that is equal to x dash. X dash is given by L minus x. Then the displacement of the particle P due to the reflected wave becomes, the reflected wave is traveling from the point B and reaches the point P to reach a distance equal to x dash in opposite direction. Therefore, the displacement is y2 is equal to a sine 2 pi by lambda into Vt minus L minus x dash. This value of x dash is given by L minus x. Now, on simplification of this term, Vt minus L is minus 2L. Minus into minus is plus. It is given by plus x. Therefore, it is given by Vt plus x minus 2L. Therefore, the displacement is y2 is equal to a sine 2 pi by lambda into Vt plus x minus 2L. Let us call this as the third expression. Now, this direct and reflected wave gives rise to the formation of stationary wave. Then, the resultant displacement for the stationary wave is given by y is equal to y1 plus y2. And that resultant displacement is given by y is equal to a sine 2 pi by lambda into Vt minus x plus a sine 2 pi by lambda into Vt plus x minus 2L. Now this term can be expanded by using the formula sin C plus sin D. That is equal to 2 sin C plus D by 2 into cos C minus D by 2. Where C is given by Vt minus x and D is given by Vt plus x minus 2L. And C plus D by 2 is given by C is Vt minus x plus D is Vt plus x minus 2L by 2. That is here, this value of x cancels. Then Vt plus Vt is 2Vt. Plus into minus is minus 2L divided by 2. Here, when I take 2 common, this value of 2 cancels with 2 in the denominator. We get this as Vt minus L. Therefore, C plus D by 2 is given by Vt minus L. Similarly, C minus D by 2 is given by Vt minus x minus d is Vt plus x minus 2L divided by 2. Here the term such as Vt cancels. Minus x minus into plus is minus x. So minus x is minus 2x. Minus into minus is plus 2L. This is given by 2L minus 2x by 2. When I take 2 common, that cancels with 2 in the denominator, you get that as L minus x. Therefore, C minus d by 2 is equal to L minus x. Now, on substituting these values of C, d and C plus d by 2 and C minus d by 2, we have A sin 2 pi by lambda into Vt minus x plus A sin 2 pi by lambda into Vt plus x minus 2L. This is the term to be expanded. On expansion of this term, we get that value as equal to 2A sin 2 pi by lambda into Vt minus L into cos 2 pi by lambda into L minus x. Therefore, the resultant displacement of the stationary wave is given by y is equal to 2A sin 2 pi by lambda into Vt minus L into cos 2 pi by lambda into L minus x, which is an expression for stationary wave. Thank you.